Welcome back. This is Mr. Wakefield looking at Chapter 11, the last chapter in Math 71. We're going to have two sections in Chapter 11, 11.1 right now, and 11.4 in the next video. In 11.1, we have this thing called an infinite sequence. We just call it a sequence for short. Okay, all sequences basically are going to be infinite. Okay, doesn't mean that we always use all the terms in the sequence all the way to infinity, but sequences basically are infinite, though, meaning that they go on forever. In fact, look at what this says here. It says that it's a function. I'll talk about why it's a function here in a second. But a sequence is a function whose domain is a set of positive integers. Positive integers are what? They are the positive whole numbers. Okay, for example, 1, 2, 3, 4, 5, 6, 7, 8, all of those numbers. Okay, starting with 1 and just all the whole numbers after that. Remember, domain is the numbers that you plug into the f of x if it's an f of x function. Okay, so we call this thing here a sub n. That's just like f of x. For example, back when we first learned about f of x, we had, for example, I'll just give you a basic version of it. Say you had f of x equal to 6x minus 3. Okay, and then you would plug numbers into that. You could plug in 1, for example. If you plugged in 1, it would be what? It would be 6 times 1 minus 3. If you plugged in 2, it would be 6 times 2 minus 3, and so on. Okay, what does that have to do with a sub n, though? A is just like the f. It's the name of the function. The n is just like the x. It's the variable where you plug the number in. Okay, so if you had, for example, a sub n instead of f of x, it would be something like this. Okay, instead of 6x minus 3, it would be 6n minus 3 because, again, the n is the variable that you plug into. Okay, so just like 6x minus 3, it would now be 6n minus 3. And then a is the name of the entire function, just like f was before. Okay, so if you wanted to know what a sub 1 is, and again, I call it a sub 1 because the 1 is underneath the a, so we say sub for it being underneath it. But it just means that that's the number you plug in. That's all that it means, okay? So that would be, again, just like with the f of x, it would be like this right here. Okay, if you wanted to do a sub 2, it would be 6 times 2 minus 3. Okay, so it's a very similar thing to f of x. Then that's why they call it a function. Okay, but all of these numbers could be plugged into it. Notice it says it's just these numbers, though, that are in the domain. So you're never going to be plugging in 1.5 or 4/3 or something like that. It's always the positive whole numbers. Okay, and it creates this sequence of numbers. I'll talk about that more as we go along here. Let's jump into the first one here. Here's our first sequence formula, which is a function formula. And it says write the first 4 terms of the sequence. What they mean by first 4 terms is since the domain is 1, 2, 3, 4, 5, 6, 7, and on forever and ever, the first 4 terms then would be when you plug in 1, 2, 3, and 4. Okay, and that would represent the first 4 terms. That means that if you wanted to know the 5th term of the sequence, you do a sub 5. If you wanted to know the 10th term of the sequence, it would be a sub 10, and then you plug in 10, for example. But since they want to know the first 4, this is what we're going to plug in. Okay, 1, 2, 3, and 4. Let's see how it comes out. Okay, so in this first one here, we get... again, when you have a fraction with no variable in it and they want you to figure out what the top and bottom are equal to first, okay, and then put that fraction in lowest terms at the end, and that'll tell you what the fraction is equal to. So it reduces down to 1/2, doesn't it? Okay. Next one. Figure out what the top and bottom are equal to, and we get 6/7. Keep going here, a couple more. If I plug in the 3, I get 9/8. Again, that's already in lowest terms. And then finally, a sub 4. You get 12 on top and 9 on the bottom, which reduces down to 4/3. Okay. Now, why do they, if this is just a function, why do they call it a sequence then? Well, you may have heard of the word sequence in outside of a math classroom. Like, for example, you might hear them say, we have a sequence of events that are occurring. Okay. Things follow a certain sequence. That's another phrase you might hear. Things follow a certain sequence. What does that mean when they say that word? Okay, sequence has to do with patterns. Okay, for example, a sequence of events taking place might mean that there's a certain pattern to the events that are taking place. And so when you have a sequence, all right, there's a certain pattern that develops. It's not too easy to look at the lowest terms fractions, but just the original fractions here. If you look at that, you can see a pattern developing: 3 6, 6 7, 9 8, and 12 9. The pattern that I see there is that the numerator keeps on increasing by 3 each time, doesn't it? 3, 6, 9, 12. Whereas the denominator does what? It keeps on increasing by just 1 each time. So the numerator increases by 3. The denominator increases by 1. With that in mind, what does it appear, according to the pattern that's developing, what appears to be the next term? Well, I would think that it would be 15 tenths. At least it's 15 tenths before you put it in lowest terms anyway. And the reason why is because you would expect the numerator to increase by 3 and the denominator to increase by 1. Now, you should always double check by actually plugging 5 in here to find out, but that's what you would expect it to be. And if you do plug in 5, that's exactly what it's going to be, 15 tenths, and then you would reduce the fraction. But that's the whole thing about sequences, and that's why we call it sequences. A pattern develops here as you go from one term to the next in the sequence. Let's do that again. Again, the first 4 terms. So if we plug in 1, okay, we got to do order of operations again. As we've seen before, though, with order of operations, if you actually have an operation such as addition, for example, we've seen multiplication before inside of an exponent. Now we see addition. You got to figure out what that exponent's equal to before you can actually take something to that power. In this case, -1 to that power. As I've mentioned before, and I'll mention again, when you have a operation inside of an exponent, it's as if there's an invisible parenthesis around that exponent. Okay, so just like this is a parenthesis right here, this is kind of like a parenthesis too. You don't have to write this, but it's like there's an invisible parenthesis around that. And it reminds you that since both of these things are parentheses, essentially, and since they're separate from each other, you can do them both at the same time. That's how you do the parenthesis step in order of operations. If you have more than one parenthesis, but they're separate from each other, you can do them both at the same time. Okay, you don't do the -1 parenthesis because that's already done. That's just a single number inside the parenthesis, so that parenthesis essentially is done. But these other two, because they're separate, you can do them both at the same time. So that's what an exponent is if you have an operation inside of it. It's like a parenthesis in that sense that you need to get done before you can do the exponent. In other words, -1 to that power. So what is -1 to that power? -1 squared is 1. And so then we have 1 times 5 is 5. Let's do that again. A2. -1 to the 2 plus 1 power times 2 plus 4. Again, you have to do the exponent. You've got to figure out what it's equal to first. I'm not talking about -1 to that power, but to actually figure out what the exponent is first before you actually take -1 to that power. I get 3, and I do that at the same time as the other exponent there, which is 6, because those two things are separate from each other, but we think of the 2 plus 1 as a parenthesis around it, just like I did up here with the 1 plus 1. Then we do the exponent, actually take -1 to that power. That's equal to -1. Negative 1 to the third is negative 1. And then we multiply by 6 and we get negative 6. A couple more times here. Following the same idea that we just talked about in the previous two parts. Okay, figure out the exponent at the same time that you figure out that parenthesis. Okay, and then negative 1 to the fourth power is 1. 1 times 7 is 7. What do you think the next term is, just based on the pattern that's developing here? 5, negative 6, 7. I would think that it would be negative 8, okay, because the number itself keeps on increasing by 1, but the signs seem to be alternating here. Let's find out if that's really true or not. Again, don't automatically assume it's going to be what you think it is. Double check to make sure, but it does look like it's going to be that way, and we would expect that sequences to follow patterns. All right. So that's probably what it is. Negative 1 to the fifth is negative 1. Remember, when you take a negative number to an odd power, it's always negative. Okay. So it's not a surprise that's negative 1. And then multiply by 8, you get just what we thought it was going to be, negative 8. So what do you think the next term would be if they asked us for that? It appears that it would be positive 9, and then after that negative 10, and then after that positive 11, and so on down the line. Okay, and it follows that pattern, all right, as a sequence normally would. Okay, one more here. What does that thing in the problem there that looks like an exclamation point, what does that mean in math? It doesn't mean the same thing it would in an English class, for example, or any language class for that matter. Okay, and that's nothing to do with getting excited, okay, as an exclamation point would imply usually. Here's what it is. Let's go up here. The explanation point, as we normally would call it, is called a factorial in math, a factorial. Instead of showing you this theoretical looking thing right here, let's jump right to some examples. 5 factorial would be 5 times 4 times 3 times 2 times 1. 7 factorial would be 7, 6, 5, 4, 3, 2, 1, all multiplied. In other words, the number that goes with the factorial, okay, that number, what you do is you always start out with that number, and then you just go down by 1 each time until you get to 1. And then you multiply all those numbers together. That's how a factorial works. So if it's 0 factorial, I know that doesn't seem like it makes sense, because how could you count down to 1 if you start with 0? Okay, well, you can't, but it's kind of like when you have something to the 0 power. As we've talked about many times before, if you have something to the 0 power, that doesn't seem to make sense either, does it? Okay, how do you take something to the 0 power? How do you multiply something 0 times? But yet we still have an answer for that, and it's the same answers we have here for 0 factorial. It's equal to 1. Okay, so 0 factorial is equal to 1, just like 4 to the 0 power is equal to 1. So good thing to remember there as well. We'll need that for later. So with that in mind, let's try this out. And as I do this first one, you guys, I need to remind you, since we've never done factorial before, factorial, when we do order of operations, is in the same category as exponents, meaning that we need to do parentheses before the factorial, just like we would do parentheses before an exponent. But then we need to do multiplication after the factorial, again, just like you would with an exponent. Okay, you always do multiplication after an exponent. So this is how it works. We do the parenthesis first. The other thing that makes factorial similar to exponents is that when you have a parenthesis next to a factorial, it applies to that parenthesis but nothing else. Okay, so the factorial does not apply to the negative 2, just to the 2. Okay, so if you have a parenthesis next to the factorial symbol, just that parenthesis is what the factorial applies to. So in other words, they just want you to take the factorial of 2, not negative 2. What is the factorial of 2? Well, 2 factorial, okay, same thing as 2 without the parenthesis there, but the parenthesis tells us that it only applies to the 2 and not to the negative 2. But what is that? That is just 2 times 1, isn't it? Okay, again, you start with the number and then you count down to 1. Well, there's not much of a way to go there, right? Okay, 2, the next number is 1. But that's how it works. Just like up here, when it was 5, it was 5, 4, 3, 2, 1. So if it's just 2, then it's just 2, 1. Okay? So 2 times 1 is 2, and therefore 2 factorial is equal to 2. And therefore my final answer here, as I finish it off with multiplication, as it says here, negative 2 times the bracket, so that's multiplication there. That's going to be negative 4. Okay, let's keep going. Next one. Again, parenthesis first. And then since factorials are in the same category as exponents, you do the factorial after the parenthesis and then the multiplication last. So don't do negative 2 times 3. You'd be going out of order. Factorial first, but the factorial only applies to the parenthesis 3. What is 3 factorial? 3 factorial is 3, 2, 1. 3, 2, 1. 3 times 2 times 1 is what? It is 6. 3 times 2 is 6. 6 times 1 is still 6, right? And there we go. Next one. Following the same pattern here. Parentheses, we get 4. Factorial, 4 factorial would be 4 times 3 times 2 times 1. If you figure that out by just multiplying 2 numbers at a time, 4 times 3 is 12. 12 times 2 is 24, and then times 1 is still 24. Then we finally multiply by negative 2 at the end, and we get negative 48. Last one here, we again parentheses first, and then 5 factorial is 5, 4, 3, 2, 1. Okay, we have that right up here, and again, you multiply 2 numbers at a time. Anytime you got a bunch of numbers being multiplied, no other operations like addition or subtraction or anything else, just multiplication. Okay, just a bunch of numbers being multiplied, you multiply 2 numbers at a time. 5 times 4 is 20, times 3 is 60, times 2 is 120, and then times 1 is still 120. So we get 2 times 120 here, which is negative 240. Okay. Okay, so what I'd like you to do right now, and you don't have to do that thing here where you ask yourself what the next number is. You can if you want. Okay. But let's move on here to the next set of problems here. I'd like you to try these now. They're very similar to what we just did. Certainly there's some differences. But go ahead and try those and then hit the play button. We'll take a look at the answers. Number 1. Okay, if we plug in, let me zoom out just a little bit here. There we go. If we plug in 1, 2, 3, and 4, this is what we get right here. What 4 answers do we get? We get 1, 5, 9, and 13. As you'd expect, you would think that the next number is going to be 17, wouldn't you? Because it just seems to keep on increasing by 4 each time, doesn't it? Okay. And sure enough, if you plugged in 5, we would get 4 times 5 minus 3. And yes, that is equal to 17. Next one. If we plug in 1, 2, 3, and 4, this is what we get. This time the exponent is just a single number. You don't have to compute the exponent this time. So that means we just do the parenthesis first. There it is right there, 5, 6, 7, and 8 for each one of those. Then we do the exponent for each of those. And we get negative 1, 1, negative 1, and 1. All right, all depends on what the exponent is there when negative 1 is your base that you're taking to a power. And then finally multiplying, and we get this right here. Very similar to problem B. It's just that the signs are a little bit different. But you'd expect the next number in the sequence to be negative 9, wouldn't you? Okay. It's always good to check that to make sure, but That's what it appears to be, isn't it? Finally, number 3, before we flip over to the back side of the worksheet. Okay. Plugging in everything. This is what we get right here. All right. And remember, when you have a fraction and you want to do order of operations, and we need to do order of operations again because there's no variable anymore on this side of the equal sign, and we want to figure out what these things are equal to so that we'll know what A1, A2, A3, and A4 are equal to. So order of operations says to figure out what the top and the bottom of the fraction are equal to. Let's get started on that. The bottom, you just have to do an exponent, 1, 4, 9, and 16. The top, though, you got to do your parenthesis before the factorial like we talked about. So I did my parentheses, and then my factorials end up being 2, 6, 24, and 120. Okay. So those are your fractions. Then you put them in lowest terms after you figure out what the top and bottom of the fraction is equal to. And these are the 4 answers you get when you put them in lowest terms. Okay. All right. Moving over to the back side of the worksheet, before I actually look at that, we need to talk about this thing here. It's a Greek letter, and it's called sigma. Sigma, S-I-G-M-A. Okay, and it refers to adding up things in math. Okay, so when you see that letter, sigma, looks kind of like an E, doesn't it? But it's called sigma. It's a reference to addition. Addition of what, though? Well, notice here that on the bottom they have 1. And it says I right there. I want to clear something up right now. We've talked about I earlier this semester in reference to imaginary numbers. When you see I underneath a sigma or next to a sigma, like right here where it says AI, okay, when it's used as part of a sigma letter, or summation notation is another way of referring to the sigma letter, when you see it used with summation notation, it is not an imaginary number. It is just a normal variable. In any other time in Math 71 besides summation notation, if you see the letter I, okay, it is in reference to an imaginary number. Okay, just here, it is not. And so just think of it as a variable here. Okay, so they're saying instead of AN this time, it's AI. It's just the same thing as AN. It's just that they changed the letter of the variable to I instead of N. One of the reasons why they did that is because they wanted to put an N up here. This is not meant to be a variable here, though. This is actually going to be a specific number, and I'll talk about that here as we go along here. But the number down here is where you start, and the number up here is where you end. So you start at the bottom, you end at the top. Okay, what do I mean by that? Here's what I mean. Let me show you as I flip it over to the back side of the worksheet. I'll show you a sample problem. See how the bottom number is 1 and the top number is 6? Okay, that means that they want you to do this. They want you to plug in every single number, whole numbers that is, okay, not decimals or fractions like we talked about earlier. Don't do that. When they want you to plug in all the whole numbers from 1 to 6, as you can see, I'm setting that up now. And then what does it say after that? It says to add them all up. You can see that they mentioned that here in the formula. See how it says that they're adding up everything here? Okay, that's what they're saying. So it's very similar to what we just did, where you just plug in a bunch of numbers, but you start out with this number to plug in, you end with that one, whatever those two numbers are. And then after you figure out what these things are equal to, you add them all up, all of them. Okay. So for example, on the next one, see how it says 1 on the bottom and 4 on the top? That means that you're going to plug in 1, 2, 3, and 4, and you're going to stop at 4. And then you're going to add up those things. See on this problem, it starts at 0 actually, and it ends at 4. That means you're going to plug in 0, 1, 2, 3, and 4. Those 5 numbers, including the 0. And then again here, you're going to do the same thing as on problem D. You get, since it goes from 1 to 6, you're going to plug in 1, 2, 3, 4, 5, and 6, ending at 6. And then add up all of that stuff. Okay, so let's give this a shot here. What do you plug into? You always plug into the thing that's right next to the sigma letter here. All right, and so plugging in 1, I get 5 times 1. All right, I didn't give myself enough room here. Hold on. That's going to be equal to 5, isn't it? Okay. For 2, you get 5 times 2 is 10. So just like on the front side of the worksheet, plug it in and then figure out what each term is equal to. The difference, though, this time is you're going to be adding them up at the end. Okay. So A4, 5 times 4 is 20. A5, again, you're plugging into the 5i formula, or the 5i expression there. So 5 times 5 is 25. And finally, 5 times 6 is 30. So what we need to do now, you guys, is we now need to add up all of these things. 5 plus 10 plus 15 plus 20, all the way up to 30, like that. And so when you see the sigma letter and they say find the sum, unlike the problems on the front side, we're actually going to have just one answer because they want us to add it all up and get one answer out of it. So yes, we got 6 answers in the first part of the problem, but because we're adding up everything, it's going to end up being one answer, and that answer is 105 when you add up those 6 numbers. You can put those in your calculator, and 105 will be the answer that you get. Okay? All right, let's try this one now. To make some room here, I'll kind of go off to the side here. But we want to plug in what? We want to plug in 1, 2, 3, and 4, right? Because it starts at 1 and it ends at 4. Let's see how that comes out. On the top, we get -1 to the, and that's a, you know what? I just noticed something. I apologize. There is a misprint here. Please change those N's right there to I's because when you have an I on the bottom here, that means that's a variable you plug into. All right, you probably could have guessed that we were supposed to plug into N. All right, so I'm not overthinking this here. It's just to be official here. We want that to be the right variable there. So that's I plus 1 there, and then this is 2 to the I power. Okay, so please make that correction just to be completely thorough there. That should be -1 to the 1 plus 1 power. And then underneath that, that's 2 to the first. I'll figure out what that's equal to in a moment. The next one here is -2 to the 2 plus 1 power over 2 to the second. Again, the I is 2. A couple more here. -1 to the 3 plus 1 power over 2 to the third, right? And finally, -1 to the 4 plus 1 power all over 2 to the fourth. Let's see what all of this is equal to here. Again, when you have a fraction and you're doing order of operations, figure out what the top and bottom are equal to. Remember, you got to figure out what the exponent is before you can take -1 to that power. So I got -1 squared over 2, which is 1/2. Okay, next one is going to be -1 to the third, which is -1. All right, over what? Over 4, right? There we go. And then next one is -1 to the fourth over 8. So that's going to be +1 over 8. And then the last one is -1 to the fifth, which is -1, over 16. What happens when you add up a bunch of fractions, you guys, as we finish it? Remember, we got to add up all these answers, right? That's what the sigma letter means, right? I need to make some space here as I talk to you about that. We need to add up all these things, and when you add up fractions, you need a common denominator. So we got a little bit of work to do here still, okay? The common denominator, though, is actually 16. 16 is the smallest number that is a multiple of 2, 4, 8, and 16, okay? And so Remember, how do you figure out LCD when you just got single term denominators like this? Okay, especially if you don't have any variables, you just have to look at the biggest number, 16. Okay, and what are its multiples? 16, 32, 48. Okay, 16 times 1, 16 times 2, 16 times 3. But 16 times 1, the very first multiple of that biggest number, 16, is actually going to work for all the rest of them. Okay, because all of these numbers divide into 16 evenly. 2, 4, and 8 do. And so that's why I picked 16. So I need to multiply by the appropriate things like I always do when I'm adding fractions in order to make all of the denominators the same. And that last denominator already is the correct thing there, 16. So what do we got here? We got 8/16, negative 4 over 16, 2 over 16, and negative 1 over 16. Remember, you're adding, okay? So what do we got here? We've got 8 plus negative 4 is 4. 4 plus 2 is 6. And then 6 plus negative 1 is 5. And remember, when you're adding fractions, okay, the denominator stays the same. You make it the same and then it stays the same. Okay, so that is the answer right there, 5/16 on problem E. Okay, so please right now, you guys, please try 4 and 5. You'll notice they're very similar to what we just did. 7i is very similar to 5i. And then number 5 is very similar, and then it's a fraction, so you're going to have to do some least common denominator work at the end of that problem there, just like we did here, okay, with the red pen right there. So please try 4 and 5, and then once again, hit your play button. We'll take a look at the answers. Okay, so number 4, we're going to go every number from 1 up to 6, right? Starting with 1, ending at 6. And so plugging in every number from 1 to 6, we get these 6 answers right here, which come out to be these 6 numbers. But again, that's not our final answer. They did not just ask us to find the first 6 terms of the sequence. This is not a question like the one on the front side of the worksheet. No, the sigma letter tells us to do more than just find the 6 terms. They want us to add up those 6 terms after we find them. So doing that, we end up with a final answer of 147. Okay, so add them up when you see that sigma letter. Number 5. Okay, in this case, we need to plug in everything from 0 to 4. All right, that means 0, 1, 2, 3, 4. Those 5 numbers get plugged in. Okay, and this is what it looks like, at least initially. Okay, then you start to compute it. All right, fractions mean you figure out what the tops and bottoms are equal to, and then you put them in lowest terms. Okay, these are the 5 fractions I get. But because I need to add them together, I need a common denominator. Again, the 120 will be the common denominator. Okay, you don't need to look at bigger multiples of 120. But again, what do we do when we have just constant terms as our denominators? You take the biggest number, 120, and you list out its multiples. Okay, 120, 240, which is 120 times 2. 360, which is 120 times 3. Fortunately, I don't have to go through this list beyond just the first number, but that's what you would normally do. If 120 doesn't work, you go to 240, and then you go to 360 if 240 doesn't work. But because 120 works, okay, then we can use that. All right. In other words, 120 is a multiple of all these other denominators. So I multiply by the appropriate things, as you can see I did here, in order to make the denominators all the same. And then once they are all the same, then you add up the numerators while keeping the denominator the same. If I do that, I end up getting negative 76 over 120. Now that I've just got a single fraction as my answer, as usual, we put it in lowest terms, okay, unless they tell you to do something different. But they didn't here. They didn't say anything about making it into a decimal or anything like that. So you can just put it in lowest terms. That's fine. And negative 19/30 is your answer. Okay, so that is sigma notation. Speaking of sigma notation, summation notation also is what it's called. If you come down here to the last set of problems, we're going to be going backwards now. All right. Notice it says express the sum in summation notation. So what they want you to do actually is see how the answers here look like. This looks like something you would get when you actually start adding the terms together. Now that's the beginning of the problem. And then what they want you to do is they want you to end up with this as your answer here. They want to know what sigma notation or what summation notation that this thing right here came from. Here's what they want. They want you to take a sigma letter, and it's got to be equal to this, okay? But they want to know what summation notation this is equal to. So in other words, they want to know what number you start with, what number you end with. Remember, the number you start with is on the bottom. The number you end with is on top. So in other words, what number would you plug in first and what number would you plug in last? And then what actual math expression would you actually plug those numbers into? Okay, here's how you do it. Let's look at what we've got up here. We're adding up 3 to the first, 3 to the second, 3 to the third, and then ... just means it follows that same pattern. So the next term will be 3 to the fourth, and then 3 to the fifth, and then 3 to the sixth. And ultimately, it would go all the way to 3 to the 14th power. Okay? So what's the common pattern there? Let's look at that. Notice that the 3's stay the same, don't they? If you've got something that stays the same, we call that constant, right? And so when you figure out what you're supposed to plug into, you would think that the 3 would be constant. We don't want to put a variable there where the 3 is supposed to go because that 3 stays constant. Okay, you don't want a variable where there's supposed to be a constant. So since the 3 stay the same, I'm going to keep that as a 3. So that's the base. That's the thing that's taken to the power. Okay, what's the thing that changes, though, in these different things? 3 to the first, 3 to the second, 3 to the third, and so on. It's the exponent that changes, right? So it makes sense that I would put an exponent, or pardon me, I would put a variable where the exponent is located. So the 3 stays constant, the exponent does not, and so I put a variable in the exponent, but not where the 3 is. Okay? So here's the question now. If that's going to be the thing I plug into, let's make sure it comes out right. We want to have a number down here so that if I plug it in, it's going to give me this first term. Remember, this number down here is supposed to give you the first term, and this number up here at the top is supposed to give you the last term. Okay? So isn't it true that if I plug in 1, I get 3 to the first, which is the first term right there? So it makes sense that 1 would be the first thing you'd plug in. And then you plug in 2, and then you plug in 3, and you get 3 to the second and 3 to the third, and so on. But what we're concerned about right now is, what do I put up here? Well, what's the last thing I would have to plug in order to get 3 to the 14th? Wouldn't it be 14? Okay. So that's what they want. They want you to write down the sigma letter, and then they want these other 3 things. They want the number on the bottom, they want the number on the top, and then they want the math expression that you actually plug those numbers into. And there you go. Let's try that again right now. Again, since they want you to write it in summation notation, write down your sigma letter. Okay. And then they want those 3 things. They want to know the number on the bottom that I is going to be equal to that you plug into I. They're going to want to know the number on top. And then they're going to want to know what expression you actually plug these numbers into. This one's the opposite. This time the exponent is the one that stays constant, right? 5, 5, 5, all the way down here is still 5. So it makes sense then that the exponent stays as 5. But what is the base? Well, the base changes, doesn't it? 1, 2, 3, all the way up to 9. And so it would make sense then that the base would be where your variable goes. And so it looks like I to the 5th is the correct choice. Let's double check to make sure here as I figure out what the bottom and top numbers are going to be. If I plug in a number to get 1 to the 5th, what number would that have to be that I plug in? Wouldn't it be equal to 1? Isn't it true that if I start with 1, I'm going to get 1 to the 5th right here as my first term, which I need to. I need the first term to be 1 to the 5th that I'm actually adding here. Remember, the addition symbols are just separating the terms that you figure out because you're supposed to add up all of the terms. Okay? That's what summation notation means. What's the last number that I would have to plug in? Well, if I end up with 9 to the 5th and the expression I plug into is I to the 5th, doesn't that mean that you're supposed to plug in 9? Okay. And so there you go. Again, figure out the bottom, figure out the top, put the I down here as well. That's just how it's written, I equal to 1. And then figure out what the expression is that you plug into. Let's do that one more time. Okay, so this time we got a fraction. When you got a fraction, you guys, on each term, what I'd like you to do to make it easier on yourself is split it up into the numerator and denominator separately. Okay, you'll notice that both the numerator and the denominator, they both change. And so both the numerator and denominator are going to have a variable in it because they both change. Okay, but notice that on the top, it's just 1, 2, 3 all the way up to 11. So if I start out at 1 like I do more often than not, okay, if I start out with 1, wouldn't I be the correct thing to put up there? Because if I plug in 1, I get 1 on top. The next number I plug in would be 2, and I would get 2 on the top. So I is the perfect choice right there. But the bottom is different. Okay. If I plug in 1 and I get 4, and if I plug in the next one, which is 2, I would get 5. And then the next one, which is 3, if I plug that in and I get 6, doesn't that mean that the denominator is always supposed to be 3 more than what I plugged in? Okay. 1 gives me 4. 2 gives me 5. 3 gives me 6. Okay, what does 3 more than mean? It means that you're going to add 3 to the number you plug in. Okay, and since I is where you plug the number in, it would make sense that you would add 3 to I because it's supposed to be 3 more than what you plug in, which would go right here. The number you plug in will go right here where the variable is. Okay, so I plus 3. If this had been 2 more then you would say I plus 2. Okay, for example, if the denominator was 5 more than the number you plug in, okay, then it would be I plus 5. All right? So what is the last number here that you're going to plug in? What number would go on top, in other words? Let's take a look here. Okay, if I plug in 11, all right, wouldn't I get 11 and 11 plus 3? And that would be 11 over 14, wouldn't it? Again, the last number you plug in has to match up with the last thing that you're adding here. And so that's why this would have to be 11. Okay? And there you go. Please try those last 3 problems here. They're very similar here. In fact, they kind of give you a clue here where it says 16 and 16 plus 2. Same thing as 16 over 18, but they're just kind of cluing you in on how the formula is going to work there. But give that a try. And then hit the play button. We'll take a look at those answers. Number 6. Again, you write down your sigma letter. Okay. And then you look at each term that's being added here. Okay, again, we saw this in problem G up here, where this time the base changes, but the exponent stays the same. So since the exponent stays the same, that's going to be a constant number, 4. And so put a 4 for the exponent. Since the base changes, I'm going to put a variable right there. I'll choose I. It doesn't always have to be exactly I. As we found out with the denominator in problem H, sometimes it's slightly different than I. Like, for example, it could be I plus something. Okay, but more often than not, it's I. So try that first to see if it works. And as you'll see here, it will work, because if I start out with 1, then I get I to the 4th. Perfect. That's exactly what I wanted here. I to the 4th is the first term. And then the next number I plug in is 2, and then you get 2 to the 4th. So everything's working here, right? The next number would be 3. I get 3 to the 4th. Everything is going according to a plan here. But what's the last thing? It's 12 to the 4th. So that means that the last number I have to plug in is 12, right? Because then that would give me 12 to the 4th when I plug 12 into here. And there you go. Number 7. What would you plug into? And then we'll figure out what numbers we're actually going to plug in. Again, very similar to problem F up here. Okay, this time the base is constant, but the exponent changes. So since the base is constant, 5, 5, 5 all the way across, that means that we're going to have 5 as a base. And then since the exponent changes, that's where I'm going to put the variable I. Let's see if it works. If I plug in a 1 first, doesn't always have to be 1 first all the time. Sometimes it could be different. But does that work here? Yes, it does. Because if I plug in 1, I get 5 to the 1st, which matches up with the first term. So that must be a good choice then. And then the next number I plug in would be 2, which would give me 5 squared. And then the next one would be 3. That would give me 5 to the 3rd. So everything is matching up according to what I have here. Everything's going fine. But then where is it supposed to end? It's supposed to end at 5 to the 10th. And the only way you can make it end there is if you make this top number equal to 10. Because if I plug that in, I get 5 to the 10th. One more to go here. Just like problem H right above it there, we got a fraction. And not only that, but the fraction has a numerator and denominator that both change as you go from one fraction to the next out of all those fractions you're adding up. So very similar to problem H. The top is 1, 2, 3, 1, 2, 3, and then it follows that pattern. So it would make logical sense that you would make the top of the fraction I, because usually you start with 1 and then you plug in 2 and then you plug in 3. And so you want the numerator to be that same thing that you're plugging in. And when you want something to be exactly the same thing as the number you plug in, you just make it equal to I, not I plus 3 or I plus 4, just I, okay? Because I is the thing you plug into. But then notice the bottom here, very similar to the problem up here. Up here, the denominator was always 3 more than the numerator, wasn't it? It was always 3 more than the number you plugged in. And that's why I said I plus 3. Well, this time, the denominator is always what? It's always 2 more than the numerator. And it's also 2 more than the number you're going to plug in if you start out with I equal to 1, which we always should try to start out with I equal to 1 to see if it works. We can always change that if needed, but to try that. And so if I start out with I equal to 1 and I use I up here, which is going to make it 1 and 2 and 3 on the top here, 1, 2, 3, just like you have here, 1, 2, 3 on top. In a similar pattern here, the bottom is going to be what? It's going to be, if you plug in 1, you're going to get 3. If you plug in 2, you're going to get 4. If you plug in 3, you're going to get 5. Notice again that the denominator is always 2 more than the number you plugged in. And since that's the case, you're going to say I plus 2. If it's 2 more than the number you plug in, which is represented by I, okay, then you just say I plus 2. Just like up here when it was 3 more, you said I plus 3. Okay, so let's see if it works now. Let's make sure our numbers that we're plugging in work here. For 1, I get 1 over 1 plus 2. That's 1/3. It fits perfectly. If I plug in 2, I get 2 over 2 plus 2. That's 2/4. Again, it fits perfectly. Okay, so everything's going according to pattern, but what would have to be the last number that I plug in up here in order to get 16 over 18? Okay, it would be 16, wouldn't it? Because if I plug that in, I get 16 over 16 plus 2. See, they even clue you in on that by writing it as 16 plus 2, but it's actually equal to 18 on the bottom here, right? the point is that if I plug in the 16, I'm going to get 16 and then 18, which is exactly what this is. And so 16 is the correct choice for the bottom, or pardon me, for the last number. For the last number that goes on top there, okay, 16 is the correct choice. So that concludes section 11.1, an introduction to sequences, okay, and also summation notation, okay. Let me know if you have any questions about that. Other than that, we have just one section left, section 11.4, so we'll get to that in the next video. But again, let me know if you have any questions, and you have a good day, and we'll see you back for section 11.4.